Okay, so we have started recording, and for backup, okay, we are set now. So in the previous week, we were discussing about stress. We started with the concept of traction. We went on to a more general discussion of stress, and then we started discussing about the transformation of stress. And the way that we proceeded in that previous chapter on that previous topic of stress and stress transformation was quite a bit deviated from the way that it was presented in our textbook by Beer Johnson and others. That was necessary because I wanted to present to you a more general the concepts from a more general viewpoint, so that in the future when you go on to study more advanced topics, it won't seem like a completely alien different chapter. That was my intention. In a similar vein, in this particular topic also that we are going to start today, strain and strain transformation, my perspective of the matter is similar. In the book, in our textbook by Beer Johnson, the things have been presented. Of course, the derivations are correct and everything. There is no problem with that as such. I mean, even if I don't teach you, I ask you to just read the textbook. I mean, all of you will be able to understand what is written in the textbook. But the problem is that at the second year level, you understand it, that is fine. But when you go on to more advanced things, and mind you, even before you go on to more advanced things, I'm expecting that the more academically serious amongst you will be starting their various academic projects with various professors. And when you start your projects, you will invariably have to start reading research papers. Now, the way that those research papers are written, like in the area of solid mechanics, they certainly involve the discussion of stresses and strains, and invariably you will find that there is a massive disconnect between the way it is presented in your textbook and the way it is discussed in those research papers. That is why I thought that it will be a good idea if I, Nikhil, do you want to say something? Nikhil Gupta, you're unmuted. If not, please mute yourself. All right, thank you. That's why I wanted to present it in a way so that it is not exactly the course content from the subsequent courses which you will be studying in your advanced years, but it will give you a general enough understanding of the overall thing. Okay, so you will see that I will deviate quite a bit from the way it is presented in our textbook. Okay, but if you can just wrap your head around it a little bit with some little bit of effort, you will tremendously be benefited. So with this background, let us start our discussions. Okay, so just like in stress, we started from a very basic, fundamental idea of the concept of traction. In a similar way, when we want to talk about strains, we want to start our discussion not directly from strains, rather from a discussion regarding the overall deformations that are occurring in the body. Now, when we do that, let me go to the writing app. When we do that, we will consider a general three-dimensional body, just like we had considered in the case of traction when we were introducing the concept of traction. So we will say that we have this general three-dimensional body, and we'll consider various points within it. Now, back in stress, we had taken a plane here and cut it and done everything. But here our first concern will be with the concept of general deformation. Okay, we would like to consider how do you track the deformation of this thing. So when we are talking about all of these things, you will see that at least the students who have been studying fluid mechanics especially, you will see that there is almost a one-to-one correspondence between between some of the topics that I'm going to discuss, some of the concepts that I'm going to introduce, and what you have studied in the kinematics chapter of fluid mechanics. Okay, in fact, earlier when I used to teach this mechanics of solids course to the third year students, the name of this chapter was kinematics, and it was actually the first chapter that we discussed because it is so very fundamental. So we are going to discuss about deformation. Then we are going to talk about the quantification of deformation in terms of displacements, and then we are going to introduce strains, and finally we are going to discuss the transformation of strain. However, there is a little bit of a problem which I believe all of you have figured out through the various questions I was posting in our discussion channels regarding the mathematical background that various students enrolled in this course have, coming as they are from different perspectives. So the main question which is looming in front of us is that how familiar you are with vector calculus. So the answer is that not very much. Okay, you learned things from vector calculus in a way which was necessary for you to learn from the viewpoint of learning various courses, especially physics, but it was not covered properly in mathematics. So I'm not that worried about it because we won't need too much of vector calculus here, just a little bit. However, and in that sense, it's not too bad because all of you have equally studied maths 1 and maths 2. I mean the linear algebra thing and the calculus things. So whatever you have learned almost equally in the various sections, more or less. And whatever you have not learned, all of you. But the difference, the divergence, is between the students who are taking fluid mechanics and those who are taking thermofluid science. Because I had a discussion with Professor S.N. Bhattacharya about how he's covering it. And because he has to cover thermodynamics and fluid mechanics in the same course, there's a little bit of a time constraint that he's facing, for which he could not cover the kinematics part too much. So not to worry, what I will do is, even before I get into deformation, I will give you a very, very quick like a refresher or maybe introduction to something which we will require here. So it's like this. First of all, you note that if you have any scalar quantity phi, okay, any scalar quantity phi, and this is just a quick refresher on what you have learned regarding the absolute basics of vector calculus. If you want to consider the gradient of this phi. Now the gradient of phi, this symbol, this inverted triangle, it is called the nabla. Okay, so this is delta and this is nabla. Okay. Doesn't matter, you can call it apple, orange, anything. So nabla of phi, so what does this nabla signify, this gradient signify? Well, it is basically like the derivative, but it is like a vector derivative in the sense that this, if you consider this like an operator, this gradient, then, and you are working within the rectangular Cartesian coordinate system, then it is, the meaning of this is like this: del x operating on whatever it wants to operate on, I hat, plus del y j hat, plus del z k hat. Okay, because I am from the eastern part of India, I call this partial derivative as del. Maybe people from South India will call this as dou, no problem. So when this gradient operates on this phi, what you just have is that this is like this. Okay, it simply operates on that thing. Now phi here is a scalar function. Okay, so phi by itself will be a function, or it can be a function in general of x, y, and z. So you'll have non-zero values of this del phi, del x, del phi, del y, del phi, del z. All this is very easy to understand. Now, in terms of your actual strength, which lies in the linear algebra part, because you have done quite a bit of matrices, this gradient of phi, this can be equivalently represented in matrix notation. So if you write something like this is equal to del phi del x in the first row, del phi del y in the second row, and del phi del z in the third row. And this is a column matrix. 3 rows and 1 column. Okay, so had it been just like a v vector where this was vx I hat plus vy j hat plus vz k hat, you try to think of it in that fashion. Okay, no matter whether there is partial derivative or ordinary derivative, whatever is there, the coefficient of I hat, it goes in the first row, the coefficient of j hat goes in the second row, the coefficient of k hat goes in the third row. That's all there is to it. It's just like a vector. Now, even though we started with a scalar quantity, when the gradient operator, which is like a vector operator, it operates on this scalar quantity, the resulting entity, the result that you obtain, that is a vector. It is very important to understand this. Okay, it's very easy to understand it, but it's very important to understand and remember it. So our initial entity was a scalar, and when you are making this gradient operate on that scalar, it becomes a vector quantity. Okay, remember this. Now the question is, and this is where things become a little bit, such that we have to be careful about it, is that suppose we ask the question that what is gradient of a vector? Okay, so please note that this is the gradient symbol and this is the vector. What is this result? Now, you can try to think of it in different fashions. Perhaps you can try to think of it as del del x of v vector plus del del y of v vector plus del del y z of v vector. But then what happens to the I, j and k? Or you can think of it like this, that this is the gradient operating on the vx, the gradient operating on the vy, the gradient operator operating on the vz. So there are at least two different ways of looking at this same entity. But you understand that, somewhere at the back of your mind or somewhere in some corner of your brain, you may have a suspicion that there is like two vector quantities involved. This is the vector quantity, the operator itself is the vector. It's like a double vector. Okay, so this kind of a thing, it is also like the tensor of order 2. Okay, so earlier we had mentioned that a stress is a second order tensor, and you had no idea like what is the implication of that second order tensor. Just a name. I could have called it a second order elephant or a second order tiger, but it is a second order tensor. In a similar fashion, this also is a second order tensor. And again, I am not going into the discussion of what a tensor is and all those things. We simply don't have the luxury of time for that. But you get a feeling that at least here, just like in the concept of traction or stress, just like you had to deal with two different directions, here also you were kind of dealing with two different directions, because you have a set of three directions associated with this v vector, and you have a set of three directions associated with this gradient operator also. So it's kind of like three different directions operating on three different directions. Something is going on. Maybe there is a thing like 3 into 3 times is equal to 9 different things that you have to deal with. And indeed that is so. So instead of going into too much mathematical formalism, let me write out to you what is the result of this thing in the matrix representation. And by doing that, you will immediately understand a lot of the things which there is to understand behind its meaning. So it's something like this. You understand this v vector has vx, vy, vz. Now, the way that we expand it is to write something like this. Maybe it will be better if I go to the next page.
Excuse me, sir.
Yes.
So I have a little doubt, sir.
Yes, tell me.
So can you go to previous slide?
Yeah.
So actually here we consider that gradient of phi and that matrix. So there is no need to multiply that column vector with a row vector having I, j, k cap. Because if we do that, then we will get the above equation, that gradient of phi is equal to del phi by del x I cap plus del phi by del j cap.
Please say that again.
So am I audible now?
Yeah. No, you were audible before. I could not understand what you were saying.
So actually that matrix representation you showed.
Yes, this one, right?
So that's the column vector. Should we not multiply it with row vector I cap, j cap and k cap?
No. So it is like this. When you want to write it out in full, then you have to write these unit vectors. So it's something like this. You see, when you have a v vector, then its equivalent matrix representation is simply this, right? Vx, Vy, and Vz. So there is no doubt in your mind that this is a vector, and this is the equivalent matrix representation of that, where there are just 3 rows and 1 column, Vx, Vy, Vz. Okay, here we do not multiply anything like the I, J, and K, right? So either you go by the I, J, and K representation, or you go like this.
Okay, sir. So I mean, it is standard form that if we represent a matrix in column vector, then it is a vector.
It is a vector. It is a
IJ.
vector.
Okay.
Yes.
Okay, sir.
Yeah. So in some contexts or in certain books, but very rarely you will find this. What they do is they want to represent a vector not as a column vector but as a row vector. Okay, logically there is nothing wrong with it, because in a row vector also you have 3 elements, 3 columns and 1 row. That is perfectly fine, but this is the more common thing. Okay, usually in almost all textbooks you will find this. When I say textbook, I don't mean Beer and Johnson. Okay, so advanced textbooks.
Okay, sure.
All right. So we were going to discuss the expansion of this in the matrix representation. Let's do that. So gradient of this v vector in the matrix representation. So this is del Vx del x, del Vx del y, del Vx del y. Sorry, del z. This is the first row. Second row is, I guess all of you can now figure out what this is. This is the thing. Okay, so this is a general vector. In the context of fluid mechanics, it can be the velocity vector. In the context of our mechanics of solids, this will be our displacement vector, and we will deal with it. So this is the overall representation. Please note that in the first row, in the numerator, you have Vx, Vx, Vx. And the difference is in this partial derivative terms. Okay, this is del del x, del del y, del del z. Similar is the pattern in the other 2 rows. This is the thing. This also is easy to understand. Okay, you just have to remember this thing. It's quite easy to understand. All right. Now, there is something critical here. Well, you see, suppose you have 2 vectors, A vector and B vector. Okay, A vector and B vector. And you want to take a dot product between them. So please note that the way that I'm kind of presenting you these things, it's in a very haphazard fashion. Right now, you may seem that I have gone completely mad, like arbitrary things I'm discussing here and there. Okay, this is like switching TV channels when you are extremely bored. You're sitting in front of your TV and you're half asleep and you're just like mindlessly surfing through the channels by pressing your remote control. It is like that. It may seem like that. Okay, I'm arbitrary things I'm discussing one by one. But when I actually start discussing the topics, you will see how these arbitrary things fall into place one by one again. So have a little patience with me. So we are discussing this dot product now. In terms of the matrix representation, how do I write this? Tell me. You know that.
So we multiply with a trace of.
You multiply the matrices, but how do you multiply the matrices? So see, it's like this. If I individually write this A vector and B vector, okay, Ax, Ay, Az, these are the 3 components. And beside it, I will just write this thing. Bx.
So we take the trace of B vector. I mean, matrix. Sorry, transpose.
Transpose into B.
Transpose.
Transpose of B vector or A vector?
So B.
No, not B. If you take the transpose of the A, you will see that this will become a row. So this is Ax, Ay, Az, and then Bx, By, Bz, and then you multiply it. The result will be Ax, Bx plus Ay, By plus Az, Bz. Okay, you can check for yourself. If you, if you do the transpose of this thing, the second one, you can still do a matrix multiplication in terms of the number of rows and columns. It is perfectly consistent, but the resulting entity will be a 3 by 3 matrix. Okay, just like this, it will be a 3 by 3 matrix if you take the transpose here. Okay, and that also has a mathematical meaning, but that is not the dot product, because you note that the dot product is a scalar quantity. You see, this thing is a scalar. It is not a vector. It is just one term here, right? And if you do the transpose here, the resulting entity will be a 3 by 3 matrix, and you can suspect that that will be basically a matrix representation of a second order tensor, completely separate thing. All right, now we go on to something more interesting. Maybe I take the entire page here. Why am I doing like this? Okay. Next, what I want you to consider is this thing. Suppose I tell you that you do the matrix multiplication like this. Not the matrix multiplication, there is some entity which is like this. A dot gradient of V vector. Now what is this? What is this? First of all, you tell me whether this resulting entity, I don't want you to give me the answer of what the answer is, like AX, VX or whatever it is. I don't want you to give me that answer. I want you to answer me that if I ask you that this is a scalar or a vector or a tensor of order 2, what it is? What is the correct answer?
So it's a vector.
It's a
vector.
It is a vector. Okay, it is a vector entity. What it is, the result is, right now I don't care. It is a vector entity or it's a tensor of order 1. Now, why do you say that this is a vector entity? What is the motivation behind that?
So by multiplying, we'll get a 1 by 3 matrix.
What will you multiply? You tell me very specifically, okay? As if you are teaching a first year student this, like that you tell me.
Sir, I multiply the transpose of A with the delta of V vector, a nabla of V vector, then I get a matrix of I get a row matrix with the 3 columns.
So this is from the voice I am guessing this is G Venkata Sai Saran, right?
Yes, sir.
All right. You are saying this. You will do the transpose of this and then
multiply it with the vector representation of
gradient of this one, right?
Yes, sir.
Okay. Anyone else has any other opinion?
So we can write it as AIBIJ.
No, don't bring in index notation, okay? Because some of the sections of fluid mechanics, they are emphasizing a lot on index notation. Some other sections are not. And the thermofluid science guys are not at all doing this index notation, okay? So please don't bring that, okay? Had I wanted to bring index notation, I would have started with index notation in the 0th chapter itself. I am completely doing away with the index notation this time for the benefit of everyone.
Sir, excuse me, sir.
Yeah.
Sir, I have one more logic behind calling it as a vector entity.
Okay.
So the nabla of a vector V is a second order tensor, and we are taking a dot product with a first order tensor or a vector. Okay. So the total order will be decreased by 1. So for suppose if we are taking dot product of 2 single order tensors, we will get a scalar. So it is of order 0.
You are right, yeah. But partially. It's actually what you are actually saying is it should be 1 plus 2 minus 1 dot product means 1's contraction, that is minus 2. The result is 3 minus 2 equal to 1. So it's a tensor of order 1, that's a vector entity. But that is out of the syllabus of what we are discussing, okay? So please stop, don't say those things. What you have said, this one, I'm taking it but I'll come back to it. Anyone else has any opinion on how I should go about representing it to understand why this is a vector? Don't bring in index notation, all those things. Talk within the context of what we have been talking about. Suppose, so Venkata Saisaran, he said this. Suppose I say that I want to write it like this. Is this resulting entity a vector entity or not?
Yes, sir, it is a vector entity.
First of all, you tell me how many rows and columns are there in the way that you have written this thing. How many rows and columns will be here?
So for Nabla V, it will be 3 by 3, and okay, for the final result.
Final one, what will it be? Will it be
1 by 3?
It will be 1 by 3. Okay, so please note that there is a little bit of a discrepancy here. Okay, because according to our previous discussion, the matrix representation of a vector entity should be 3 by 1, not 1 by 3. So this is like a row matrix. Okay, so right there you have a little bit of a problem. Now you can say that, okay, I'll take the transpose of that entire result. You can do that, but it's still a little bit problematic. Think about this. How many rows and columns are there?
3 rows.
3.
So it will be 3 by 1.
It will be 3 by 1. So from at least that perspective, this seems to be on the right track. Suppose I said this. Any problem?
No,
This
sir, it will be the same.
Same.
It will be also 3 into 1. Now what the bloody hell is going on? Okay. So if you're feeling like that, good. You should feel confused. Okay. If you have a false feeling of false feeling of confidence right now, shed that. You are supposed to feel confused at this point. Okay. It's good to feel confused like this. You see, all of these are actually vector entities. Okay. That part is correct. So what Venkata Saisaran said is correct, like that. There is a little bit of a problem in the sense that it is turning out to be a row matrix, but we can of course fix it by just saying that it is like that. Okay, just a small adjustment, and then that thing gets corrected. So it becomes like that, ulta. This is also giving 3 into 1. This is also giving 3 into 1, which is the correct one. Okay, it cannot be arbitrary like this, because if you do the calculations and write the results, the X, Y, and Z components of each of these things may turn out to be different. They are not going to be equal. Certainly not. Okay, so
I think the last one is correct.
Last one should be correct. Yes.
you think that the last one is correct. Okay, I'll tell you the answer. This is wrong. This is wrong. This is correct. Which is why I actually made it a point to discuss this at length. I have spent half an hour without going into the actual deformation and displacement, but this is the correct one. Okay. Now, again, I'm telling you, you're supposed to feel confused here. Let me point out something. If we go back, go back. So this one, this gradient of V. Okay. So you see here that when we were talking earlier about the V vector, it was Vx, Vy, and Vz. Okay, it was like this. But here, when you are talking about the gradient of V, all the Vx are in the numerator, but what is appearing like this gradient vector, the del x, del y, and del z, they are appearing in the first row itself. They are not appearing in the first column, which is why ultimately when you write the thing, this is not the correct answer. Rather, this thing will give the correct answer when it is like this. Okay, so beyond this, I will not invest any more time. If you want to have a further discussion regarding this, the discussion channel will be perfectly open. We will continue our discussions there. Right now, I want to stop this discussion with the mention that this is the correct thing, and this will be actually important later on. Okay, later on means in the discussion of strings. I guarantee you that I am leaving you deliberately dissatisfied with this current level of exposition. Feel confused, feel frustrated, and post your frustrations and discuss and whatever you want to ask in the discussion channel. I will try to answer to the best of my ability, because I have practically condensed about a week words of lecture in this half an hour of discussion. Okay, for the lack of time, I have done that, but I have done this deliberately because for most of you, you will never ever require this. Okay, maybe just a handful of students will be interested in this, will require this, and that kind of discussion is actually within the scope of an advanced course, not this course. But we will go forward with what we need. So let me now go back to what we were discussing with regards to deformation. First of all, for deformation, we will consider a very general point. A general point like this. Okay, and we will call this general point or the position vector of this general point with reference to a general coordinate system, as we had been talking about earlier, this x, y, and z. And I will call this position vector x vector. In fact, it will be better if I call this as capital X, capital Y, and capital Z. Okay, you'll notice in just a short while why I'm saying that. It makes a little bit of a difference, the way that I'm going to write it. Okay, so let it be capital X, capital Y, and capital Z. This is capital X, it's like this. And then what I say is that under some amount of load or some distribution of load on this three-dimensional body, let this three-dimensional body undergo some kind of deformation. Okay, it may change shape, it can move from one point to another, this entire thing. So after the deformation has taken place, let the shape of the body be like this and let it be positioned somewhere else. Okay, like this. And then in this deformed state, let the position vector of the same point that we were considering earlier, that generic point that we were considering earlier, let the same point be now here. Let it be here. Let it be called P dash, and let the position vector of this be given by the small x vector. Please note that this is a capital X vector. This is a position vector. Okay, so position vector with reference to this origin. This is the small x position vector with reference to this origin. Fine. Now, I know in every batch of students, there are a bunch of students who do not make any distinction between when they are writing on a piece of paper between capital X and small x. They just write it like this. Please do not do this. Okay, this will be completely, horrendously confusing. Okay, just try to write it like this. Okay, like a proper cursive X. Okay. Now, this is all there is to the deformation part actually. Okay, now what we'll say is that this position vector, x vector, that will be a function, and that will be a function of the initial position vector as well as of time. But since we will be dealing mostly with statics, we will not consider this dynamical aspect of it. We will consider that everything is taken quasi-statically. So it is like this, that the final position vector is a function of the initial position vector. Remember this, it will be of tremendous importance subsequently. And this particular relation, it is referred to as the deformation map. So it's basically mapping this kind of a relationship. It is mapping from the initial configuration, the undeformed configuration, to the deformed configuration. Okay. So next, what we want to discuss is displacement. So these are some definition kind of thing, almost like mathematical definitions. Displacement. What we do is we say our displacement we define. Okay, so here I am going a little bit mathematically formal. We don't just write this as an equal to. Okay, because an equal to denotes like a simple equation kind of thing. This is not a simple equation. This is a definition. And the way that we denote a definition is by putting a colon sign in front of the equal to. We are choosing to write our displacement vector in this particular fashion. Small x minus capital X. It's not a big deal. Okay, the way that I'm writing it, you almost know this from whatever you have studied in your high school physics. That the displacement vector is of course like this, the final position vector minus the initial position vector. But the things that we're going to do subsequently, that will have a lot of significance on a proper mathematical understanding of this rather innocent looking definition. Bit advanced. What we do now is that using this idea, this basic idea of deformation and this basic idea of the displacement definition, we go into something called the quantification of deformation. So why are making such a big fuss about it? Quantification of deformation. First we have talked about deformation. Now we are talking about quantification of deformation. What is really going on? Why are we being, this kind of a pedantic kind of approach here? You see, previously when we were talking about this kind of a deformation, we were tracking basically just a single material point as it goes from here to here. But when you track this thing, of course, you are getting the entire displacement field through your definition of U, but it does not give you a direct interpretation or a direct, like a visual kind of understanding of how different points which are located within this three-dimensional body, the relative distance between them, that is changing. What I mean to say is that if you just concentrate on this point, this point remains as a point here also. If you just look at that one point, sure you have all the information embedded in the displacement vector, but just looking at that thing, it doesn't give you a proper understanding or a visual representation of how this overall shape has changed. In order to do that, what we would like to have is some kind of a relative displacement between two neighboring points. Because if we can understand how two neighboring points are moving with respect to each other, we will have some kind, or we will begin to have some kind of an understanding about how the overall deformation is taking place. Now, what I'm saying is rather abstract to you. Let me quantify this properly. What we do is this. We again take this three-dimensional body. We again mark out a point here, just like before, P. This has the position vector X vector. And then we consider a point which is very near to P. Okay, a neighboring point Q. And let the position vector of this be X plus dx vector. So basically Q minus P is dx vector. Very simple to understand this. Now let the body deform. Please note that in this entire discussion of this topic, I am not going to be bothered with the nature of the loadings that are going to occur here. I am only interested in how the shapes are changing, how the relative deformations are taking place, all those kinds of things. Okay, so that is the way of looking at mechanics in this fashion is what is referred to as kinematics, where you are not bothered with the loadings, the forces, the torques on the body. Rather, you are only interested in the change in shapes, displacements, deformations, all those things. Okay. So in this deformed state, let it go to P dash. This P, let it go to P dash, and this Q, let it go to Q dash. Just like before, we say that this is X dash, X vector, and this one we will say this is small x vector plus d small x vector. All right. Now what we do is looking at the displacement of the point P. Now what we are going to do is we are going to look at the displacement of the point Q. What is the displacement of the point Q going by this kind of a definition? Tell me. we are looking at the displacement of the point Q. Tell me what it is.
Small x plus d small
plus d small
Yes.
minus capital X minus capital dx.
All right. So this is what we have. Now you quickly note that this small x minus this capital X, what is that?
U.
What is this thing? That is U.
U capital X.
Exactly. So this is nothing but U capital X. U. So this is U vector, function of the position vector capital X vector. So this is basically the displacement vector associated with the point P. Okay. So from here, what we obtain is this. Just a way, I mean, different way of writing the same equation by transposing the terms. All right. Now you see, this has a lot of promise. These two terms, this have a lot of promise in the sense that we can Taylor expand this thing. Okay, so I'm sure you have learned various kinds of expansions in your first year. So we are going to do a Taylor expansion on this thing. The only problem here is that when you were previously studying Taylor expansion, you were mostly doing Taylor expansions of scalar functions which are where the input was also a scalar. So basically, so let me write this thing. We were doing Taylor expansion previously, but the Taylor expansion that you are familiar with, let me use a different color for the brief refresher that I'm going to give you on Taylor expansion. You were doing some things like this, probably. F of x plus h is equal to f of x plus h by factorial 1 f dash x, where f dash is basically del f del x or df dx, plus h square by factorial 2 f double dash x plus higher order terms. This you are familiar with. Even if you have forgotten, you have studied this. Next, suppose I have f this time not as just a function of x, rather as a function of two variables. Let's say x plus h and y plus k. What is this? This is f of x plus y, f x comma y plus h by factorial 1. Let me write this properly. This is del f del x plus, tell me, can anyone tell me what this should be?
K by factorial 1 into del f by del y.
Yes, k by factorial 1 del f del y. What should be the other terms? We won't require them, but I just want to write this out.
H square.
This term will, yeah, h square by factorial 2 del square del fx del x square plus this thing will also come k square by factorial 2 del square f del y square plus you will have this term twice of hk by factorial 2 del square f del x del y plus you will have higher order terms. Finally, you're going to have, let's say, three dependencies, y plus k, and let's say, how do I write this? Hk, some, let's say m. Okay. So this will be f of x, y, z plus. So I'm going to go only to the linear terms. So h by factorial 1 del f del x plus k by factorial 1 del f del y plus m by factorial 1 del f del z plus you will have all the higher order terms. Okay. Now you compare with this thing. Okay, this is x vector plus dx vector. Okay, don't worry about the x plus dx vector. It is something like, so you understand that there are three components to it. And that is where we make a connection with this thing, because we could have very well written this like x plus dx vector here, something like that. Okay, because this will have one x component, which is x plus h. This will have a y component, which is like this. This will have a z component, which is like this. Okay, so this thing, the Taylor expansion of this thing can very well be written like I have written it here. Let me demonstrate to you by actually writing it. This u vector, x plus dx vector, what I will do is, you please note that this x vector, it is something like this, x I hat plus y j hat plus z k hat. Okay, just because I have written this thing as x, please do not be confused that this same x is appearing here. It's not like that. This is the entire vector and this is just the x component of it. You may have written this as a p vector also. Okay, it would not have mattered. Anyway, so this thing can be written as x plus dx, y plus dy, z plus dz. And now this is exactly the same as before, except that earlier it was just an f, but this is now a vector. So I now expand it. So this is x, y, z plus dx by factorial 1 del u vector del x plus dy by factorial 1 del u vector del y plus dz by factorial 1 del u vector del z plus higher order terms. Now this x, y, z, I can equivalently write this as u vector function of the general x vector. And this thing, I just write it again. All right. You can try to think of it like this. So this is one perspective I'm giving you. You can try to think of it in this fashion. See what I have written here. This is one vector. This is another vector operator. If you do the actual dot product like I have represented here, what will you obtain? Dx del del x plus dy del del y plus dz del del z. This is exactly the same thing which was present earlier. And this entire operator present within this curly bracket that is operating on this u vector. Okay, so this is one way of looking at it. Now you tell me that, okay, that this is very much possible to write it like this, that we have, so this entire thing is dx vector dotted with, and what is this del del x I hat plus del del y j hat plus del del z k hat? You're already familiar with this, tell me.
Nabla.
That is
Nabla.
Yeah. And this is operating on this u vector. Now you go back to the previous page. See what was present, where we had left it. So we had left it here. Let's copy it. Come back to the next page here. So this thing is going to be equal to what? This is dx vector. So if I substitute this ux plus dx vector from whatever we have just obtained, this is u vector x vector plus dx vector dotted with the gradient of u minus, don't forget this term, u vector x vector. So this one cancels with this and you end up with just this thing, dx vector plus dx vector dotted with gradient of u. All right. So this is your answer for the d small x vector, this entire thing. Okay. Now, written in this fashion, it is fine, it is correct and everything, but in order for subsequent manipulations, this is not really useful. It is not really useful because we are not going down the route of the index notation, in which case, if I wrote like this, the next step would have been very easy. But I am not allowing myself that freedom. I will not use the index notation. I will use something which you are familiar with, which is why I had introduced to you the various kinds of matrix representations. Now you tell me that if you go back, you see I had written this thing a vector dot gradient of v vector, and now I am getting something similar looking, dx vector dot gradient of u vector. This is exactly the same thing that I had obtained. You see this one, I'm focusing on this dx vector dot gradient of u. This is that. And I told you that the equivalent matrix representation of this thing will be this one. So it will be, according to this thing, it should be gradient of u vector, no transpose business, times dx vector. Okay. Now, some of you may be a little bit unhappy with the fact that here, in order to arrive at this kind of a vectorial representation in terms of dot products and vectors, I had interpreted this term in terms of a dot product between these two things. But now when I'm writing the matrix representation, I want to take this thing together with this thing. Okay, there are other ways of writing this thing. Okay, so there are other ways of interpreting this thing. I'm not taking that because this kind of a result that I'm writing now, that will be actually useful for me for my subsequent derivations. Okay, so let me go to that and you will see the benefit. So the bottom line is that I have this expression now. I have just a little time left, but I think I can cover this. You see, I've still not talked about strains, but I will do that. So I have this, and the matrix representation of that I am taking this matrix representation will be like this. Okay. After this, I cannot do anything if I just keep on writing like this. Okay, I have to say something new. And the new thing that I'm going to say is regarding strains. Okay, so finally we come to strain. Now for strain, what we had discussed earlier. Okay, let me not do like this. Okay, let me not do like this. What I want to say in a more general sense is that I have this d small x vector and I have this this d capital X vector. If I want to compare the relative displacement between the point P and Q, go back earlier to this diagram. Okay, I have a line segment connecting this P and Q, these two neighboring points in the undeformed configuration, and in this deformed configuration also I have this line segment P dash Q dash joining the neighboring points. And I want to get a quantitative way of representing this change. Okay, this PQ, how it is changing to P dash Q dash, I want to compare these two things. So how do I compare? I have been writing in terms of vectors, everything, but ultimately, when it comes to a quantification of the deformation, all that I want to do is I want to compare this d small x vector with this d capital X vector. This is what I want to do, the magnitude of this. Okay, this is the absolute value. This is not the matrix. Okay, this is the absolute values of dx and d capital X. So if you have a d small x vector or d capital X vector and you want to take the magnitude of that, what do? You simply take something like this. So dx vector magnitude is equal to what? It is d small x vector plus dy small y vector square plus d small z like this. Okay, and you take the square root of this. This is what you do. Similarly for the d capital X vector, you do like this, and you see this, my small z and the capital Z have gotten mixed. So maybe I'll make it a little bit curly, or I can write like this. I can write like this, and there's a square root here also. Now the issue is dealing with square roots is not very convenient. Okay, wherever the square roots are appearing, it makes life really difficult. So since our ultimate aim is to compare these two things, we might as well compare the squares of these two things. Because they involve the square roots, I want to get rid of the square roots, so I will compare this thing. So instead of this comparison, I will compare this with this. And I'm looking at the clock, my time is up, and it is a good point to stop here because I can start from a good point, from a good starting point in the next class. So class is over, all of you can leave. If someone wants to ask something, you are most welcome. Thank you everyone very much.
So,
Thank you, sir.
Sorry?
can we make one more simplification, sir? Like we can write this dx vector as like identity matrix into dx.
Yeah.
So like in the topic, so we can condense that as like I plus del u vector. I mean,
so
nabla u vector.
You want to write like this, right? Yeah, that can be done. That can absolutely be done. No problem. But we won't need that.
Okay, sir.
All right. All right, guys, please go to the next class. Thank you.
Thank you, sir.